Professor Monty. Let's talk about graphs of linear inequalities. All right, so here's my key ideas. The first one has to do with whether the line is solid, meaning the line is part of the graph, or the line is dotted, meaning the line's a boundary, but it's not part of the answer to your problem. Okay, so remember, when we graph lines, the line is a picture of all the solutions. So anytime I have an equals in there, that means the line's part of the solution. I'm going to have a solid line because it's part of our answer. But if I have a strict less than or a strict greater than, the line's just the boundary. It's not part of our answer, so we draw that with a dotted line. Okay, so remember, if it has an equal, solid line. If it doesn't have an equal, dotted line. Okay, now next, since we've got inequalities, anytime I have a less than, whether it's a less than or a greater or equal to, I'm always going to shade below. The shaded region is my answer. So I'm going to have an infinite number of solutions. I can't list all the points that make the inequality true, so I shade the region. So graphically, we can see, oh, if it's in the shaded region, it's part of the answer. So a less than or equal to, shade below, greater than or equal to, shade above. So we'll talk about that as we do some examples. Let's get into those. So the first one, y is less than 2x minus 1. The first idea is just to graph that. Since it's already set up kind of in slope-intercept form, I'm just going to graph it that way. So I've got my numbers. I've got -1's my y-intercept. My slope is 2. Remember, think of that as 2 over 1. So I go up 2 and I go right 1. Well, that's going to be my line. So I'm going to draw that line through those 2 points. It doesn't have an equal, so it's a dotted line. So I draw a dotted line up through here. And we can label these points if we want to. I'll label them in just a second. But since it's a less than, I shade down, because the y value less is going to be below. So I shade down this one. That's actually my answer. Any value in that shaded region works. And I'm going to check a number. Notice 0, 0 is not in my solution. So 0, 0 shouldn't solve this. So check 0, 0. So I'm plugging it in here, and let's see what I get. See if I get a true statement or not. So x is 0, y is 0. So I go 0 is less than 2 times 0 minus 1. 0 minus 1 is just -1. 0 is not less than -1. That's false. So 0, 0, not in answer, meaning not in the shaded region. And notice, there's 0, 0. It's not in the shaded region. So I've checked, at least I know that point shouldn't be shaded, and it's not. Okay, so if you're just using the ideas of less than, shade below, that worked out, or you can always test a point. All right, let's do this one. There's a little more going on over here. So I may just find y-intercepts and x-intercepts to see what this point is. You can graph it that way, but then you can't use the above and below. You'd have to test a point in that case. But if I solve this for y, so I can use slope-intercept again, I'm going to subtract the x. So I get -3y less than or equal to -x plus 6. But now I divide by -3. And remember, when you divide by a negative, you have to flip over the inequality. So now it's a greater than or equal to instead of a less than or equal to. These negatives cancel out, but remember that's a 1 up there. So let's just call that 1/3 x. And then 6 divided by -3 is -2. So now when I graph, I'm going to say, okay, my y-intercept's -2. My slope's 1/3, so I go up 1 and right 3. And then there's going to be my graph. This time I have an equal, so it's a solid line. Because again, the line's part of the solution. Now I have a greater than, now I shade above. So any value, any point in that shaded region is going to make this inequality true. Also, any point on the line itself makes it true because of the equals. And again, let's test a point. Here's 0, 0. This time it's in the region, so it should be true when I plug it into the original inequality. So again, let's check 0, 0. Again, that's x, that's y. I'm just going to plug it in. So I get 0 minus 3 times 0 less than or equal to 6. Well, that's all just 0. 0 less than or equal to 6? Yeah, that's true. So 0, 0 in solution. I guess over here I wrote in the answer, in the solution, in the shaded area, however you want to say that. So 0, 0 is in the shaded region. As long as I graphed my line correctly, then I've got the right answer. And then this one a little bit different because I can't set it equal to y, so I can't have any y equals, slope-intercept form and graph it that way. So let's just think of a couple points for the line itself, x equals 0. So remember, x equals 1. So x equals 1, they don't tell me what y is. I can pick anything I want to for y. So if I draw this graph and I go over to 1, 0, and I go to 1, 1, oh, it's a vertical line. Remember, anytime you have x equals, it's a vertical line. There's no equal there, so it's still vertical line, but it's dotted. And it's greater than, well, if this was x is 1, a number greater than 1 might be 2 or 3 or 4 or 5. So if it's just x greater than, it's going to be to the right. So my shaded region is this way. Again, you could check 0, 0. 0 greater than 1, oh, that's not true. It shouldn't be shaded, and 0, 0 is not shaded. Okay, so that's how you graph linear inequalities. I will link to this the graphs of systems of linear inequalities so you can see how that goes. Okay, but practice these. We use these not terribly often, but periodically they come up. We need to know what they mean. So hopefully that helps. Now you know how to graph these and find the solution.